So moving right along, we're going to be going into the quantum theory. We're going to be learning about quantum theory of the atom, and this is where we're going to more focus in more on our electrons. So let's forward through all that and get over here. All right. Basically, when we just start thinking about the quantum theory, this is just kind of a little history part that I'm not going to ask you a whole lot about, but there was a man named Niels Bohr. Now, Bohr correctly predicted the frequency lines in the hydrogen's atomic emission spectrum. He correctly predicted it based on the amount of energy, the quanta, that little packets that we talked about, that hydrogen would absorb and its electrons absorb up to higher energy levels and then release. That's how he correctly did that. So the lowest allowable energy state of an atom is called its ground state. So for hydrogen, when it's not releasing any colored light or anything, that's just at its ground state, all the electrons are in the lowest possible energy level. So when an atom gains energy is when it jumps up into a higher energy level. So Bohr suggested that an electron moves around the nucleus only in certain circular orbits. So he's saying that an electron has a certain road that it can take, and it can't ever get on any other road around the nucleus. So each orbit, or each road, was given something called a quantum number. So the first orbit in Bohr's theory was quantum number 1, and it corresponded to energy level 1. And then the second was 2, 3, 4, as we go up in energy levels according to what Bohr said. So hydrogen has 1 electron. It's in the n equals 1 orbit in the ground state. So when energy is added, that 1 electron moves up to the n equals 2 orbit. So here's a picture of kind of what Bohr's model of the atom was. So you see the center orange dot. That orange dot is your nucleus, that positive center there. That's your nucleus. And you can see that the electron first lives in that n equals 1 spot. Well, when it gains energy, it absorbs these little packets, these quanta of energy. Then it'll jump up. And as it jumps up into the 7th, 6th, 5th, and 4th energy levels, they'll emit different colors of light. These different colors, if you see over here, this section here, are the colors that you saw on that atomic emission spectrum that I just showed you. And here it is again to kind of show you. So the ground state is 1. Down here at the bottom. When energy is added, they'll jump all the way up to the 6th level, and when the 6th comes back down, it emits a purple, and when it jumps to the 5th and comes back down, it's this blue, and then it's this kind of blue-green, and then it's this kind of red, depending upon what energy level the excited electron jumps to. That's Bohr's model of the atom. Now, his model explained hydrogen spectral lines, but he could not explain any other atom spectral lines using this theory. So at this time, after Bohr's theory and the whole atomic emission spectrum with the hydrogen, the behavior of electrons still was not fully understood. Okay, it's known that they don't move around the nucleus in circular orbits. So what's going on with these electrons? So then along came this man named Louis de Broglie, and he had a hypothesis that particles, including electrons, could also have wave-like behaviors. And he did all kind of stuff, and yeah, you don't even need to know about all the different things that he did, but he helped contribute to what we know an electron now. And then another contributor, whose last name was Heisenberg, showed us that it was really impossible to take any measurement of an object without disturbing this object, and that it's really impossible to know precisely the velocity and the position of this particle at the same time. And the only quantity that can be known is the probability for an electron to occupy a certain region around the nucleus. So when we say that an electron is like in an s orbital or a p orbital, which you're going to learn about shortly, it's really only the probability that is in there, and that's according to Heisenberg. So we have Bohr, we had de Broglie, we had Heisenberg, and we had this other guy named Schrodinger who treated electrons as waves, and he had this quantum mechanical model of the atom. Well, all these guys compiled together in all of their different hypotheses and their research and stuff. So it came back down to the fact that electrons and quantized energy. De Bohr orbits explained hydrogen. De Broglie led scientists to think of electrons as both particles and waves. Schrodinger, his wave equation predicted the existence of atomic orbitals containing electrons. So all of these guys contributed to what we now know and what we study and how electrons are arranged in the atomic orbitals. And these electrons, for ones that have more than one electron. See, Bohr was great for one electron, but then once you start adding more electrons, things get kind of hairy. And so it was the contributions of all three of those that actually helped us now learn how we study where electrons are positioned around a nucleus and how they orbit in an atom. So the principal quantum number, which we're going to be talking about now, talking about these electrons, where they are in orbit, they have particle functions, they behave like particles, they behave like waves. These principal quantum numbers, they're going to indicate the size and the energy of the atomic orbitals. And N, for the quantum number, is going to be the principal energy level for our orbitals. And you'll see what I mean as we start looking at a periodic table. So, in each level, there are sub-levels contained within the principal energy levels. So, if you think about it as like this picture here gives you kind of stadium seating. So, in this level, this first floor here is the first level. And if you start filling this auditorium, you're going to fill from the bottom here, going all the way out to the back. We're going to fill in the first row, then the second row, then the third row, and then the fourth row until every seat is taken. So in this first energy level, there's only one sub-level. And in the second energy level, we have 3 sub-levels, like sections at a concert. And in the third level, now you've got 3 sections. And in the fourth level, you have 4 sections. And all of this is also seen in our periodic table. Now, each one of these sub-levels, each one of these sections contains these orbitals. And these orbitals have different shapes. Our s orbital, that very first floor section, our s orbitals are shaped like spheres. You see over here, they're kind of these round spheres. And then when you get to our p orbitals, they're more shaped like dumbbell shapes. These are our p orbitals here. We have 3 p orbitals. Now, each one of these orbitals hold 2 electrons. So this one s orbital can only hold 2 electrons. That's the maximum occupancy of that orbital. Now, each one of these p's can only hold 2 electrons as well. So in the p orbital as a whole, there are 6 electrons, each 2 electrons traveling a certain road. This electron travels this road, these 2 electrons would travel this road, and they never cross over. They don't go on each other's roads. Well, don't want to go back, I want to go forward. So this table is just basically talking about hydrogen's first 4 principal energy levels and the quantum number and how many energy levels that you can have in each quantum number. And I think it makes more sense for us to look directly at a periodic table to be able to understand this. So I want to skip over to understand exactly what I'm talking about. If I can get over there. is we're going to look at the periodic table, we're going to look at these quantum numbers, we're going to look at these orbital shapes, and our goal is to figure out the electron configuration. We want to take all the information that Bohr and Heisenberg and Schrodinger and de Broglie, all the information that these scientists worked on, and determine, where do these electrons live? Where do they live around the atom? Because where these electrons live helps govern the chemical behavior of the atom, and the chemical behavior is what we are going to be studying about. So it's important for us to know where they live. We're going to do this. We're going to look at these quantum numbers and the s, p, d, and f orbitals and study something called the off-ball principle. The off-ball principle states that each electron occupies the lowest energy orbital first. Off-ball is the German word for to build up. When you're building a house, you don't put the roof on before you lay the foundation. We have to lay the foundation of our electrons and then build each level. So off-ball is to build up. We are going to be building up these energy levels, these sub-levels, these orbitals, and putting electrons in. Now this sheet is not in your unit guide, this graph here, but I'm going to give it to you because a lot of students find it helpful in how to learn how to build up. Just as when you build a house, there are certain things that you have to do first. You have to lay the foundation, and then the next step, and the roof is the last. We have the same sort of steps in filling up our orbitals and filling up our electrons around the atom so that we can study the chemical behavior of an atom. So this particular image there will be very helpful to you as you start to study how to build up our atoms. So we're going to be looking at this off-ball principle, and we're going to realize that all orbitals related to an energy sublevel are of equal energy. So that means you just saw that we had 3 of those p dumbbell-shaped orbitals. Each one of those 3 p dumbbell-shaped orbitals can hold 2 electrons, but each one of them are the exact same energy. No one of those p dumbbell-shaped orbitals is any greater energy than the other. But the p orbitals themselves are of a higher energy level than the s orbital. So, let's see. Whoops. Oh, I was trying to go back. Okay, so now it's 2 more principles so that I can put it all together for us as we learn how to build up our electron configurations and know our quantum numbers and our sublevels and our orbitals and our sublevels. You have 2 other principles or rules. The first one is the Pauli exclusion principle. Okay, it states that a maximum of 2 electrons can occupy a single orbital, but only if the electrons have opposite spins. That will come into play. The Pauli exclusion principle comes into play when we do our orbital diagrams, which I'm going to show you. And another important rule that you need to keep in your pocket is Hund's rule, and it states that single electrons with the same spin must occupy each equal individual orbital before additional electrons with opposite spins can be added to that same orbital. Now you're looking at me probably at this computer screen thinking, lady, you have lost your mind. But I want to get to, let me move over to, okay, the best way to look at these quantum numbers, these orbitals and stuff, is to look at a periodic table, because we are going to be doing electron configurations of different elements. We're going to say where the electrons live. And the way we're going to do it is we're going to first look at our periodic table, and we're going to think of it as a hotel. And we're going to think that we have the first floor, second floor, third floor, fourth floor, fifth. Each one of these numbers going down the side over here will give you, this computer is super slow, will give you what floor you're on. Now, as you increase levels, you're increasing energy. As you're going up floors, you're going up energy levels. So for hydrogen, it has only 1 electron. Its 1 electron lives in the first energy level on the first floor. And it lives in the first room on the first floor. And there on the first floor, there are only 2 rooms available. And we have to fill those 2 rooms up before we can move to the second floor. And in each one of those rooms, only 1 electron lives. And in the first floor, the orbital is the s orbital. So our rooms are like the S wing of the first floor. And in hydrogen, because it only has one electron, then hydrogen lives the first floor in the s orbital, and there's only one of them in the s orbital. So the electron configuration for hydrogen is 1s1. That is the address for where the electrons in hydrogen live. Now helium. Helium is way over on the other side, but helium has an exception because really, this is so off calibration, helium should go over and be right next door to hydrogen. Also in the s orbital, also in the first energy level. So helium has 2 electrons because it's atomic number 2. So the first electron gets filled in the 1s1 room, and the second electron gets filled in the 1s2 room. So for helium's electron configuration is 1s2. See if the 2 comes up. 1s2. That means both electrons live in the first floor, the first energy level. They live in the s orbital, and for helium, there are 2 electrons. Now the s orbital can only hold 2 electrons, and the first floor can only hold 2 electrons because only first floor has an s orbital. So let's try beryllium. Beryllium has, here's beryllium here. Beryllium has 4 electrons. Beryllium lives on the second floor. But beryllium's 4 electrons each have to be in an individual room, so to speak. So the first 2 electrons are going to go on the first floor because we have to fill our first floor up before we can move to our second floor. Well, our first floor can only hold 2 electrons. So for beryllium, the first floor is written down, and S2 is written down for its electron configuration. But now we move up to the second floor, and on the second floor we have 2 electrons. So we include the second floor, and in the second floor these 2 electrons are also in the s orbital, and it's 2s2. The 2 comes up. That's the electron configuration for beryllium. Let's see, I'll put that over here so that you can see that. Now let's do one for nitrogen. Now nitrogen is located here. Sorry, everything's off calibration, but nitrogen is more to the left there. And nitrogen has 7 electrons because it is atomic number 7. Now each one of those electrons has to go into a room, and we have to build it up until we get the electron configuration for nitrogen. So the first floor, I'm going to do it down the bottom of your screen. The first floor, 1s2, is filled with 2 of nitrogen 7 electrons. Now we move to the second floor. Well, the s orbitals are completely full. The only s orbital in the second floor is completely full, and so that's 2s2. Now on the second floor we also have p orbitals, 2p. Now the p orbitals, we only have 1, 2, 3. So the electron configuration for nitrogen is 2p3. So when you look at the periodic table, these first 2, let me get over some, see if I can make it better. These first 2 rows, this is your s block. Your s orbital contains 2 electrons, and that is your s block. Now, these last 6 over here, excluding the helium, is your p block. Now, the p orbital has 3 p orbitals attached to it. Each one of those roads allows 2 electrons to travel around it. So you have 6 electrons total that can possibly live in the p orbital. Now our transition metals, that are all of these in between, this is your d orbital. And in your d orbital, you have 5 suborbitals that can each hold 2 electrons. So you have a total of 10. And if you count the blocks, the rooms across the transition metals, you'll see you have 10 blocks. And down at the bottom, the lanthanide and actinide series, that's your f orbital. Now it has 7 suborbitals floating around in there, and each one of those 7 can hold 2 electrons, making a total of 14 electrons. Now, I'm not expecting you to completely understand it from this video because we are going to be doing electron configurations and orbital diagrams and Lewis structures over and over and over again until we all get the hang of how to do it. What we're basically doing is kind of giving an address for each electron. Each electron has one particular address of where that electron lives.